Welcome, this is Amanda Ratkinson ZapQ, and in this tutorial we're going to focus on effect size. We're going to talk about the difference between effect size and statistical significance. We'll talk about different types of effect size, conventions for interpreting effect size, talk about how to report effect size in APA, and talk a little bit about why it's useful and why it should be reported in every article that you write. Before we define effect size and talk about the difference between effect size and statistical significance, let's take a look at some examples. Here we see a researcher found that there was a statistically significant difference between university students' course points based on the type of course that they participated in. Here we see p equals 0.03, and if you remember, as long as your p value is below the significance level you set, usually a 0.05, you can say your results are statistically significant. Now let's take a look at the mean scores between the two groups he compared. He compared online students versus residential students. In the online class, the students averaged about 895 points in the course with a standard deviation of 12, whereas in the residential class, students scored 890 points with a standard deviation of 15. So, in addition to statistical significance, we also want to take a look at the magnitude of difference in the actual score units. Here we're looking at the differences between course points. And we ask ourselves, are the course points different? The difference between the course points large enough to be of practical importance? Is one group passing the class and one not passing the class? Let's take a look at another example. This example comes from my browsing social media today. When I was browsing social media, what I found was an ad for a diet supplement. And this ad claimed that women who took this diet supplement lost significantly more weight in a 6-month period than women who did not take the supplement. So I went digging for this study since I was working on statistics tutorials today. And what I found was a study of women between the ages of 35 and 50. And what it showed was that women who did not take the diet supplement on average lost about 7.5 pounds within a 6-month period with a standard deviation of 2. Whereas the women who took the supplement on average lost about 8.1 pounds. So then the question becomes here, is it worth taking the diet supplements? Is the difference in weight large enough between the control and treatment group to be of any practical importance or practical significance? Now these two examples illustrate the difference between having statistical significance and effect size. Just because something is statistically significant doesn't necessarily mean that it's practically significant. Let's talk a little bit further about this. First of all, in any research study, we are concerned about hypothesis testing, and hypothesis testing is concerned with having a statistically significant effect. Basically, we want to know if we set the significance level at 0.05 if our p level is less than 0.05. Remember, by calculating the p level, what we're looking at is the probability of our null hypothesis being correct. And statistical significance signifies that there is a difference between the mean, and that is probably not due to chance. And whenever you do research, if you find that you have statistical significance, you, like most researchers, will become very excited. However, like we've illustrated in our two examples, research is more than just about obtaining statistical significance. Now, this is especially since probability is affected by the number in the sample. For example, let's look at the t-ratio. As long as the numerator in the t-ratio is not 0, you can obtain a t-ratio large enough to fall into the rejection zone for the null hypothesis. as long as you have a size of n that's large enough. So statistical significance is affected by your sample size. So if you gain a sample that's large enough, then you'll always have statistical significance. Now, one factor that's not affected by n, so it doesn't matter if the n gets larger, is effect size. And this is especially true with indexes of D and R, which we'll talk about in a moment. Now, what is effect size? Well, based on our examples, you probably already have an idea. But if we were to define effect size tells us about the magnitude of the relationship or difference. It gives us some practical or theoretical idea about our significant results. So now let's go back to our weight loss example and use a formula to calculate the effect size. Now, by just looking at the means, we can tell there's not a large difference. It looks like there's a very small difference between our treatment and control group. But let's go ahead and use the formula. D equals the mean 1 minus mean 2 over sigma, or the standard deviation of the population. What we do then is we take 8.1 minus 7.5 and divide it by 2, and what we find is D equals 3, which means this is a small effect size. Now, using the formula for Cohen's d, let's calculate the effect size for the second example, where the researcher looked at online students' course grades versus residential students' course grades. And let's see, is the difference between the course grades large enough to be of practical importance, of practical significance? Maybe even the university is asking the question, should we cancel one type of the course because students in another course are doing so much better? Well, let's go ahead and calculate the practical significance. D equals mu 1 minus mu 2 divided by sigma, or the means divided by the standard deviation. And I'll just note here, this is the formula for population. So there are other formulas you'll see for Cohen's d. So if we input the numbers, we find that 895 minus 890 divided by 5.68 is equal to an effect size of 0.333, which, if we refer back to Cohen's conventions for interpretation, we would say that this effect size is small, because remember, Cohen's conventions say that a Cohen's d of 0.2 is small, 0.5 is medium, so 0.3 is closer to 0.2, so we would say that it's small. The other way to looking at this is to say, since we have a d of 0.3, the two groups' means differ by a standard deviation of 0.3. Let's take a look at this graphically so that we can understand it in greater detail. So interpreting the effect size of 0.3 as small is actually done so using Cohen's conventions. In 1988, Cohen set forth conventions for interpreting the effect size of Cohen's d, and the interpretations are listed here. Here you can see a Cohen's d of 0.2 is small, 0.5 is medium or moderate, and 0.8 is large. So that you better understand this, we're going to take it a step further. Let's say if you had a d of 1, what does that mean? Well, the two group means differ by 1 standard deviation is what it means. If you had a d of 0.5, this means that your two groups differ by half a standard deviation, and etc. So if you had two groups that differed by 1.5 standard deviations, this difference would be very large, and so they would differ by 1.5 standard deviations. So that's what Cohen's d means. Let's take a look at one more example of this before we move on. Sometimes I find when we graphically represent something, it makes it a little bit easier to understand. Also, we've talked about interpreting Cohen's d as units of standard deviation. I wanted to talk about another way to interpret it, so that will these graphs will serve us well here. It's important to recognize that you can interpret Cohen's d not only using standard deviations, but also interpret it in terms of percent of non-overlap between a treatment and a control group. And Cohen, 1988, talks about this in depth. I think it's around page 21 he talks about this. And so anyway, basically what he says is that an effect size, or Cohen's d, of 0 indicates that the distribution of scores for the treatment and the control group have 0% of overlap. Now that's not illustrated here, of non-overlap. That's not illustrated here, but if it was illustrated, what we would see 0% of non-overlap is that there'd be no differentiation at all between the two bell curves. But what we do see here is that we had an effect size of 0.333, which was small. And this graphic in the top left, that's sort of a brownish color, illustrates the non-overlap. What we see is we have about a 20% non-overlap, or almost an 80% of overlap between the two groups. Now, as our effect size gets larger, what we see is that there's less overlap or more non-overlap, and that's illustrated down here in the right hand corner, where we can see that if Cohen's d equaled 1, it would be large, so that would mean that the two groups are one standard deviation away from each other, and they have about and this isn't exact, but about a 50% non-overlap, or only a 50% overlap here. So that's another way to interpret Cohen's d. Now that we've talked about Cohen's d fairly in depth, let's talk about another type of effect size often used for comparing or often used when we're comparing groups or testing hypotheses of difference. Now, there are two commonly used effect size statistics when testing hypotheses of difference. And as I just said, we've talked about one in depth, and that's Cohen's d. And remember, Cohen's d refers to the differences in groups based on standard deviations. So Cohen's d is often used when comparing two means, such as you would in a procedure like the t-test. However, some statistical analyses, such as the ANOVA, are based on proportions or on variances. So a partial eta squared becomes more appropriate. Now, a partial eta squared indicates that the proportion of variance in the dependent variable is explained by the independent variable, and the range of values for a partial eta squared range between 0 to 1. Now, since a partial eta squared is a little bit different than a Cohen's d, it's interpreted a little bit differently and on different conventions. So let's take a look at that. Here you see the conventions for interpreting both Cohen's d and partial eta squared. And what you'll notice is that partial eta squared is still interpreted as small, moderate, or medium, or large. However, the values are different here. Let's take a look at these values. A small effect size for partial eta squared is 0.01. Let's think about this and how it's interpreted, because this makes logical sense. Remember, partial eta squared indicates the proportion of variance in the dependent variable that's explained by the independent variable. This means that only 1% of the variance in the dependent variable is explained by the independent variable. Let's say we were looking at course points and how course points differ based on the type of course that students take. If we had an effect size of 0.06, this would mean or indicate that 6% of the variance in course points is explained by the type of course that students take. So this differs than the 0.01, which would mean only 1% of the variance in the course points is explained by the type of course that students take. Finally, a large effect size for partial eta squared is 0.138. Sometimes you'll see 0.14, but Cohen says it's 0.138. So that's how you interpret partial eta squared based on Cohen's conventions. Now that we've looked at the common effect size statistics used for hypotheses of difference, let's look at what's often used for hypotheses of relationship. Now, before I move on, one other note I'll make here is we're just going to talk about 3 different effect sizes. However, there are more than just 3 effect sizes, but we're talking about the most common, and these are the most commonly used. Now, for correlation analyses, the most commonly used effect statistic is the correlation coefficient of R. Now, R ranges from having no relationship at 0 to a perfect relationship of 1, and this can either be positive 1 or negative 1, and that's something we talk about further in the correlation tutorials. However, here what's important to note is that R can range from positive 1 to negative 1. And Cohen provides conventions for interpreting what these mean. Here again, whether you have positive 1 or positive 0.1 or negative 0.1, ranging all the way from positive or negative 0.2, you have a small relationship. If you have a R ranging from positive 0.30 to 0.49, you have a moderate relationship. Or if you have an R ranging from negative 0.3 to negative 0.49, you have a moderate relationship. And then for a large relationship, the range is 0.5 to 1, whether it be positive or negative. So let's say, for example, here we wanted to know the relationship between personality and, let's say, behaviors. And we find a statistically significant relationship between these 2 variables. And we find that the Pearson's R is 0.3. Well, based on Cohen's convention, we could say that we have a moderate or medium effect size. We could take this in a step further and say that, well, this corresponds to R squared, so R squared would be 0.09, which means then that personality explains about 9% of the variance in behavior, because you can square R and then you can determine the percentage of variance. Or the percentage of variance in which one variable explains another variable. So as we see here, as we're talking about this, one thing to note is this is equivalent to a Cohen's D of about a 0.5, 0.6, a moderate or medium effect size, or a partial eta squared of a 0.06. So this concludes our discussion of effect size in terms of defining effect size and interpreting effect size. Let's go ahead and move on and talk a little bit further about its usefulness. We've already talked a little bit about this because it helps us determine practical significance, but effect size can be useful in other ways too. Since effect size is useful for understanding the results, it's one of the things that APA, in addition to reporting confidence intervals and p-values, it's one of the things that APA suggests is reported in every report, every publication that individuals do. So always remember to report effect size. So effect size is important because it helps readers understand the practical significance of your results. It provides them with information so they can evaluate the magnitude or strength of the outcome. So we've established that. Effect size information can also be useful in the estimation of the statistical power for future studies, so that the researcher can estimate how large their sample size needs to be. And we'll talk more in depth about this in the power tutorial. Finally, effect size is useful because a researcher can come along and summarize effect sizes across studies, and this is called a meta-analysis. Since effect size indices such as R are given in unit-free terms or standardized terms, this makes it easy to compare effect sizes across different variables and different studies to help us determine whether or not a specific technique or teaching method or therapy technique is effective. So you can look at multiple studies and analyze the effect size to determine the overall effectiveness of a specific technique or intervention. So that's one of the most useful things about an effect size. So this concludes then our tutorial on effect size. And at this point, you should now understand the difference between effect size and statistical significance. You should understand that there are different types of effect size statistics and that we've talked about the most common, but there are some more that exist. You should understand the conventions for interpreting effect size and how to interpret effect size. When you calculate your results and you get an effect size, you should be able to explain what that means. You should understand that effect size should always be reported in any APA report, and also understand some of the uses of effect size at this point.